I first did this talk earlier today, and it was supposed to be 45 minutes, and it ran to about an hour. And even in that, I didn't actually cover all the stuff I wanted to cover. So apologies in advance. This is like, either this is going to overrun, or I'm going to just not, I'm going to miss out huge chunks of it, or I'm just going to talk really, really fast, so it's unintelligible. We'll see which one happens as we go, I think. If there were Wi-Fi, there's basically, so down there is a GitHub with all the code for the project. And to give a very, like, a broad overview, just, I got really interested in kind of AlphaGo, which, does everyone know AlphaGo? Yeah, cool. So I wanted to kind of like just experiment with some of the techniques. So I created AlphaToe, which is just AlphaGo for Tic-Tac-Toe. There's a GitHub. It's surprising how little code you need to do to reproduce kind of all of AlphaGo if it's for Tic-Tac-Toe. So yeah, so if anyone wants to get up the GitHub, I would recommend that. And also probably at the end of this talk, it won't make that much sense what I've said, and probably the code, for me, I'm an engineer, code makes more sense than someone talking to me, so try that out at the end. All right, let's start. OK, this is about AlphaGo. It's only a couple of files, which is good. Go, ancient Chinese game. Recently, Google DeepMind managed to beat Lee Sedol, who was the world's best player. This is the first time an AI has been able to do this. Quick word about Go, it's ridiculously complex. So the number of possible games is that many, 10 to the 360. Like that number doesn't exist. No one has ever written down that number. It's just some ridiculous number. And so it's more complex than chess, and it is just a hard game. Tic-Tac-Toe, luckily only about 360,000 possible games, so we might be able to solve it. Also, so Tic-Tac-Toe is a solved game. You can just solve it with min-max algorithm or basic algorithms. Just this project was, it turns out you can also solve it with deep neural networks. Is this important? No. Is this interesting? Hopefully. You'll tell me. Oh, and the other thing, so that is all the code you need to implement Tic-Tac-Toe. It's one page, which is nice. Go, you need quite a lot more to do. Why do we care about any of this? Okay, so beating board games is but also the same kinds of techniques are used in all kinds of things: chatbots, autonomous robot agents, trading systems, all sorts. And so these techniques are specifically for board games, and also more specifically kind of perfect information board games and zero-sum perfect information board games. And also when we talk about kind of board games as opposed to playing Atari games or something like that, when you're getting an AI to learn an Atari game, the rule is you're learning just from an image of the screen, and you're trying to infer how to be good at it just from those signals. In a board game, we know ahead of time an exact model of the game. We know exactly what the rules are. Our AI is allowed to simulate forward in time, so it is allowed to, given a board state, it is allowed to know exactly what a move is and what the board will look like after that move, and so on. So it kind of gives you a completely different set of problems. The problem is not about how to get a signal out of all the noise like it is in Pong. It's, you're trying to identify what particular bits of the screen matter. For a board game, we already know what matters. It's just about how do we win? How do we make the maximum mattering? Or something like that. OK, really briefly, what is the best move in a board game? We can consider a board game as a series of states. So if we start in our initial state, where there's just a single X in the middle of our board, we can then do a tree that is all the possible moves from that state. Here I've just got 3, but imagine there are 8 other possible moves there. And then you can go down the next player's move, and you can construct a whole tree of just everything that can happen in a board game up until you hit a state where one player has won and one player has lost. And in those eventual scoring states at the end, there might be values for those scores. So here are just some arbitrary values. The best move is what's called the min-max algorithm, and that is your best move is the one that leads to the worst best move for your opponent, and your opponent's best move is the one that leads to the worst best move for you. And this kind of gives a bit of an illustration here. If you're at this node and you're this player, imagine these are alternating players. Here, this player's opponent can score a 6. So the best move for him is he would select the one that allows his opponent to score the 6. At this level, this player can see, well, these are the best options that my opponent would have at the different levels. So I'm going to choose the one that leads to the worst score for my opponent, or the worst best score for my opponent, which is -6. The minus is because it's opposite players. And so that is like the value of this position, the best you could possibly do in this position. Okay, so why don't we use min-max algorithm for Go? Actually, first, why we use min-max algorithm. So the min-max algorithm, the problem is you could hypothetically construct like a massive tree for the state of any board game and get the exact best score, but that tree might be ridiculously huge. In chess, there are 10 to the power of 123 possible positions, possible games. Again, no one is constructing trees on hard drives that big. Hard drives don't go that big. So what they do is you use what's called an evaluation function. And what you just say is, what I'll do is I'll construct my tree up to a set depth, say like 8 moves, something like that. And then when I hit the 8th move, rather than continuing the tree, I'm just going to use an evaluation function to estimate how good the position is. And in a game like chess, there is a very, very simple evaluation function, which is I can just add up the number of pieces for each player. And if I have more pieces than my opponent, I'm probably slightly ahead. That is probably better for me. And so in this position, this is good for white, because white is a rook versus a bishop, which is worth 2 pawns, if you know chess. OK, so why can't we use that for Go? The min-max algorithm works. We have evaluation functions. We can just use that for Go. We can't use that for Go, because in Go, there are 2 problems. One, the state space is so much more vast than in chess. So in chess, you might have 10 to 20 moves per position. In Go, at the beginning, you've got 360 moves. That kind of averages out about 200 moves. But you can imagine 200 times 200 times 200 times 200 gets ridiculously big really quickly. And the even bigger problem than that, though, is there is no good evaluation function for Go. There is no good way to simply estimate who is ahead. You kind of have to play a game of Go through to the end to really know whether the position is good or bad for one player, unless you're a really smart human, because obviously they know better. And a good way to kind of get this across is the way that a human might learn chess versus the way a human might learn Go. So if you are a beginning chess player, you might start by playing a game, you'll play a series of moves, and you might end up in a position like this, where you're the black player, you've placed your queen there and your king there, and you've allowed a knight fork. And the knight can then move to here, and he's then going to win the queen. And a human player can look at that and go, oh, yeah, I shouldn't have put my queen in a position where it could get forked by the knight and rook. And that allows a human player to learn. A human player can go and correct that mistake and know that this is a factor that affects a winning game. When a beginning player plays Go, what often happens is they make a move, and they make a move, and they keep doing that, and then they end up with something like that, and then they add up the numbers, and they find out if they've won or lost, and they have no idea why they've won or lost. It's very hard to attribute what was the winning move. People get good at Go, and some people are really smart and will know exactly, the 12th move, he should have done something else or something. But that takes, for humans, that takes loads and loads of practice. Whereas chess, humans can learn it a lot quicker, even though to be good is still incredibly hard. So all that said, we can't use the min-max algorithm, and we need a different way in which to learn Go. So one approach, or actually, what is the simplest possible approach we could take to evaluating a position, given that the state space is so vast that we can't do every move, and that we have no evaluation function? So the simplest thing we could do is we could take a position, and from that position, we could just make random moves in different positions until we hit the end of the game. And we could just do that lots of times from the same state, making random moves. And at the end of that, at the end of each kind of chain of random moves, we could see if we won or lost, and then we'll just say the position is the average of all the results we got from just doing these random rollouts. This is called Monte Carlo sampling. And so this is a way you can evaluate a Go position. It's obviously very, very inaccurate, because to give an example back from chess, the white player here, if white is to move, this is a 1 position for white. He moves there, and he wins the game. With Monte Carlo sampling, white's only got like a 1 in 8 chance of winning, he's going to lose most of the games because black's just got more pieces. So this would evaluate wrong using Monte Carlo sampling. So the only reason we even think about Monte Carlo sampling is just because there is no evaluation function. This bit I'm going to really skip over. So basically there is an algorithm called Monte Carlo tree search with confidence bounds for trees. It basically allows Monte Carlo to converge towards the min-max algorithm over like an infinite number of plays, really, really slowly. I'm not even going to go into it. If people are interested, that's a good lecture. There's also, here's the code for it. But let's just say there's a thing that looks a bit like min-max, but not as good and takes a lot longer. That exists. Okay, so this algorithm, previous to Google DeepMind, was like variants of this were the best way to win at Go. The top Go engines use this algorithm and like modifications to it. Okay, so how are we going to improve at Go? Neural networks are cool. Everyone's using neural networks. They're great, right? We'll use a neural network. That's great. Yeah, we're all geniuses. We've chosen neural networks. I'm going to assume everyone knows what a neural network is. Everyone who doesn't know what a neural network is. Okay, everyone knows what a neural network is. Okay. Okay, so we're going to use a neural network, and who's the current best in the world at Go? It's humans. Humans are the best. So what we can do is we can just look at what humans do and just try and learn their moves. We can have a supervised network and just train off it. And this was the first step that Google DeepMind had, is they had a network. The input to the network was a Go board, a 19 by 19 board. The output was another kind of 19 by 19 board. And the output, the network is set up with like a database of Go games. And it tries to learn to predict from the state of the board what is the move that the human player would make. And it turns out with a deep neural network, I think they used about 13 layers, and it was convolutional layers as well. But with this kind of network, they eventually got to learn what move a human would make from a Go position with 57% accuracy, which is kind of huge. Like when you consider that most Go positions have 200 possible moves, 57% accuracy to pick the correct move is amazing. So that already suggests that this is a good approach. All right, now I'm going to jump back to AlphaToe. There is no database of Tic-Tac-Toe games, mostly because no one would bother. But I've got the code for how you would do this for Tic-Tac-Toe. If anyone ever finds a database of Tic-Tac-Toe games, I've got like a stub method that just throws an exception saying I have no database. But also this training, if anyone wants to do it themselves, it's exactly like the MNES tutorial example. You just replace like the inputs with the data for your Tic-Tac-Toe database or whatever game you're talking about. Okay, so we've now got a network, AlphaGo have now built a network that uses supervised learning to predict human moves with 57% accuracy. But we don't want to just like play like humans. We want to destroy humans. We want robot supremacy. So the next step is to kind of move into the domain of reinforcement learning to try and improve our network from there. Does everyone know reinforcement learning? Everyone? Anyone not? I should start with, does anyone not know? Okay. Really, really briefly, reinforcement learning is given an environment like this maze, an agent like this bunny will try and move through the maze in such a way to extract the maximum reward, such as these carrots for the bunny. And the key point, or the difficulty with reinforcement learning is that the inputs that you receive are dependent on the actions that you take. And it's very difficult to get a clear relation between the rewards that we might get and the actions that we take. It's much more difficult than supervised learning. So the approach that was used here is what's called policy gradients. How many people here saw my talk on Q-learning? Is that? Okay, just a few. Okay, policy gradients are like the alternate approach to Q-learning. And policy gradients are just kind of trying to solve quite a general problem, which is how do we maximize our reward in an environment given that we have no error function that we can train off? We're in our reinforcement learning environment, our agent is going to move through the environment and he will occasionally receive rewards, but it's very hard to attribute like which action that we took led to the reward we eventually got. and that's the best way to go from here. Okay, and so I'm just going to jump. I'm not going to explain policy gradients in too much detail, but I'm just going to show what the code looks like for them. What we're going to do is we're going to set up a network with exactly the same weights and parameters as the previous supervised network, but we're going to train it completely differently. Its output is, again, the probability of a move in any particular space on the board, given a board state. And we're going to stochastically, we're going to use that probability to draw a move from that distribution. So with the probabilities at output, we're going to choose the different moves in the different spaces. And we're going to play lots of games like that. We are going to save at each step the move we actually made. And we're also going to save at the end of the game the reward we got. And the move we actually made will look like this, a kind of one-hot encoding. Like this is the move that we randomly selected, and everything else is 0. And the policy gradient, when we times the output of our network by that, this basically acts like a mask. So we're now only going to start receiving gradient information about the move we actually chose, which is the one that actually is responsible for the reward. And then we have the reward at the end of the game, so we're going to times that kind of masked gradient by the reward we actually got. So if the reward was good, we're going to increase the probability that we select that move in the future. If the reward was bad, we're going to reduce the probability that we select that move in the future. There's a whole, but also because this is backpropagation, so we're adjusting the gradients, we're changing the things that led to us choosing that move. And the key point is, because it's stochastic, over many, many, many thousands of simulations of the game, we're going to get like a range of choices of actions based on the probability distribution. So we're going to get lots of different bits of gradient. And over a long run, it will kind of move towards the ones that so this is the first bit that I kind of really implemented for AlphaGo. So I couldn't pre-train it, so this initially just starts with like random weights. I just had it basically play games against an agent that was making completely random moves. And initially, the AlphaGo thing that I trained, it didn't even know what a legal move was. So it started off just like trying to play moves in the spots that might already have ticks or toes. Ticks or toes? Are those the pieces? Noughts or crosses? And so initially, it's got to learn the rules of tic-tac-toe first, which is like I can't make a move in a spot that already has a thing. That's choosing a move stochastically. There's code samples for all this. OK, so here's the training progress of AlphaGo. This is like a kind of normalized thing between like this is if we lost every game, this is if we won every game. So it starts off really terrible and gradually improves, and eventually gets to winning like 80 to 90% of games, which is pretty good. There's the baseline of a random agent that knows valid moves, and there's like a completely random agent that doesn't even know what a valid move is. This is all right. We can learn incredibly simple games using deep neural networks. That's the amazing achievement there. The other thing is, so it hasn't gotten all the way to 100% of wins. So there's two possible reasons for that. One is that Tic-Tac-Toe is a theoretically drawn game with perfect play. So it's possible that even the best network ever would occasionally draw with a random agent. But also, possibly, there's hyperparameter tuning you can do, and it could be a bit better than that. I don't entirely know. How are we doing for time? Good, OK. Awesome. OK, so the thing they actually did with AlphaGo is, rather than playing against a completely random agent, the reinforcement learning step, it played games against itself and historical versions of itself. So I also set this up for AlphaGo. So AlphaGo can train. It starts with a set of weights and then plays against itself, and then over time it trains new versions of itself that it plays against. There's code for this. One of the annoying things is TensorFlow isn't good at like saving chunks of the weights, so I had to do some custom functions. But that doesn't really matter. OK, so at this point, DeepMind, they've got their thing that is trained using reinforcement learning to much better kind of to play even better than just predicting human moves. It's actually beating that by quite a long way, I think. I can't remember the details. But it still could be better. So the thing I mentioned really briefly, Monte Carlo tree search with UTC, it would still be good to use that. when we're talking about our Monte Carlo rollouts, obviously a Monte Carlo rollout could be massively improved by, rather than just choosing a move randomly, you select the move that a human would most likely play. Then you're going to get a much more accurate evaluation. But the problem is, with Monte Carlo rollouts, you're normally doing like hundreds of thousands of these, and to do hundreds of thousands of rollouts, each with 200 moves, and with each move needing to be evaluated by a deep neural network, that's just too slow. We can't really do that. So an interesting approach they did is they basically trained another network called a value network, and the value network took the board state as input and had only a single output neuron, and the output neuron was just trying to predict if the reinforcement network played this game using the best of its abilities against itself, would this position be won or lost for the reinforcement learning network? And if you can get that, obviously, if this can predict this accurately, you don't need to simulate the whole thing. You just know this is going to be a won position, this is going to be a lost position. And so they did that, and eventually the error for the network was only 0.234, which is not too bad. That means it's reasonably accurately predicting what is a won or lost position. So you could now, rather than doing lots of Monte Carlo evaluations, you can just go to a few like board states and say, this is the value of this state, this is the value of this state. And so the final step, yeah, AlphaToe. So I did that for AlphaToe as well. Again, there's no database of Tic-Tac-Toe positions, so I just generated some random positions, and it can kind of learn it, but I didn't spend that much time on it because it just seems silly. And yeah, and so the final step for AlphaGo was combining the Monte Carlo tree search with the value network, and it would basically use the value network as an initial kind of probability for whether or not we should search down a given branch of the tree, and it would kind of and so it would encourage it to search around areas where it would still do the kind of Monte Carlo evaluations, but it would encourage it to search around areas that had high scores with the value network. And that overall kind of gave a mixture of basically the value network and Monte Carlo tree search gave the best performance, and that was the one that eventually beat Lee Sedol. And I've got a code example for Monte Carlo UTC. Okay, so yeah, so that's kind of the end of the talk. All the different steps from AlphaGo are implemented in AlphaToe. I've also got some other games in there like Connect 4. And also, you can change the size of a tic-tac-toe board. So there's also a game called Go Maku, I think, that's a 15x15 tic-tac-toe board. And you need to get 5 in a row, and that's actually a legit competitive game. So that would be an interesting thing to try around with. Basically, like, I think it's a fun project. I've enjoyed it. I'm very interested in like submissions or people who want to play around in this space or kind of try and beat this network. I think that would be quite fun.